Thank you for the warm introduction. I have a secret to start. I'm not an economist, so you'll have to forgive me if I don't have any of your favorite notations for you today. I do have my own notations, so I'll be sharing this with you. I originally gave this talk, the predecessor to this talk in Japan, so you may have noticed that my title is actually a haiku. So these are protocols that are used for changing Bitcoin network protocols. Unlike the previous talk, we're kind of considering a model where people do actually highly value staying together as a single chain. So we're just trying to coordinate the activation of a rule. If you've had a chance to visit an office in Silicon Valley, you might know that computer scientists really like food. And this is also kind of apparent in the terminology that computer scientists adopt. We have cookies, we have bytes, and we have famous problems that we model after eating dinner with our colleagues. The first problem in computer science, that is a dining problem, is the dining philosophers. And it's used to show how you can coordinate concurrency in programs. Later on, we also had the dining cryptographers, which are used to demonstrate the coordination of privacy among a party. Today, I'd like to share with you the dining Bitcoiners. And the dining Bitcoiners, well, this is used to show how we coordinate protocol changes. And for the dining Bitcoiners, they're all trying to have a picnic, and there are no forks on the table. And the question for them is how they coordinate what kind of utensil they should all use. So what is a fork? In the Linux world, GitHub, we know that there's a fork, and this is kind of an easy thing. You run whatever you like. You don't need to get a central maintainer's approval for something to happen. But if you did want that central maintainer's approval for it to happen, in this case Linus Torvalds, it might be vitriolic. They might be really angry. They might say, no, get your crap code out of here. We only want high quality stuff that conforms to this standard that we expect. But if you decided, well, I just want to run this for myself, you can still do that. In cryptocurrency, it's a little bit different. We all have to run the same code. If we don't, we're going to break compatibility. And so we have to get our patches, to a certain extent, merged on master in order for it to work. And it becomes extra vitriolic because we're not just trying to convince one maintainer or our own little group, we're trying to convince everyone. And there really is nobody who has that key control who can just say, this is the change that's going to happen. There are two basic types of Bitcoin fork. There is a hard fork and a soft fork. And they exist on a spectrum, but these are two useful categories to think about. In a hard fork, it's a breaking change that requires the entire network to update immediately. So an example of this is if you have a hard-coded rule that says no block may be bigger than 1 megabyte, changing it to say the block size is now 2 megabytes requires everybody to change their software. On the other hand, a soft fork is backwards and forwards compatible change, and it's only kind of an additional rule on top of the existing rules. An example of this, if we have hard-coded 1 megabyte, we can soft fork down to half a megabyte. Everybody who accepts at least a 1 megabyte block will accept a half megabyte block as well. Each of these types of fork has a pro and a con. There are trade-offs. In a hard fork, it's actually possible to get better code quality. When you're changing everything, you can get rid of a lot of the bad practices that you had in the old code base. In a soft fork, you have to maintain compatibility, so you're stuck with whatever you had before. However, in a hard fork, you're suffering from centralized decision-making, and it's impossible to make everyone happy, and especially when there's more types of changes that can happen, you might spend lots and lots of time trying to figure out exactly how things should change. Some projects that go on a hard fork basis continually debate what exactly should happen. On the other hand, in a soft fork, you don't have this coordination issue. In fact, not everybody has to even be running the latest version because you're compatible with the old one. But this does lead to some kind of weird considerations where perhaps a small majority, so like 51%, start enforcing a new rule that not everyone else is aware of, and we have some sort of closed source fork where now not everybody can get their transactions through, or they're more expensive. But because there's fewer types of change that are a restriction on the current rules, maybe there's less arguing about what exactly can be done. Other altcoins have solutions for how you coordinate these changes that are maybe worth mentioning. Tezos is built on the premise of making the entire protocol like a game of Nomic, where the rules themselves are amended in the protocol. And Stellar will prevent progress if you don't agree on what the new rule should be. And so any set that agrees, that has one of these blocking sets that agrees on what it should be, can prevent forward progress until this new change is adopted. But let's talk about Bitcoin soft forks and what they look like concretely. So in a typical Bitcoin soft fork for enabling a new feature, what you'll do is you'll take a no-op operation in the virtual machine or the script interpreter, and you will change it into something that verifies some property. So for example, you'll take some no-op operation, and you'll say you want it to check a SHA-3 hash. Right now, there's no SHA-3 in Bitcoin. And what you'll do is you will check both of those arguments, that x is the preimage of the SHA-3 of x bytes pushed on the stack, but you won't remove anything. And so from an old client, it will have the exact same execution semantics. Those two elements will still remain on the stack, and so you might just choose to discard them afterwards. Except a transaction that doesn't include the correct preimage, maybe y instead of x, that will be invalid and not be able to be included once that fork has been adopted. Peter, who you heard from earlier, made a lot of this process a lot nicer with the way that he implemented SegWit, because you can just say that there's an entire new interpreter version, and all old nodes think any interpreter version they don't know about always yields true, always gives us a valid script, and when you upgrade the client, you add one that has a new rule. And so as a user, you really shouldn't use a script version that hasn't yet been defined, because it will always be true, and you don't know what the semantics are yet. So that's a little bit on what these forks are actually doing, but how do they get made and proposed? Right now, there's two core mechanisms. One is called BIP8. This is kind of simple. Everyone agrees at some point in the future, based on height, let's say a year's worth of blocks from now, we'll activate a new rule. There's also BIP9, which is version bits. And in version bits, you have this state flow diagram where you first define a fork. Once it's kind of defined in the software that everyone's running, it becomes started at a certain time. And then you collect signals on each block to see whether or not there's enough support for the fork to activate. And you look for, under the standard version bits proposal, you look for 95% threshold of miners approving. And it's 95% threshold, but if you had a 51% attack at the same time, it would only be 51%, right? So it's 95% assuming there's no network attack. This didn't really work. So we use version bits reasonably well sometimes in the past, but when there's a controversial change like SegWit, people end up delaying this process for a really long time. Why is that? So there's this small misunderstanding in the notion of signaling versus voting. And that was kind of the key thing, I think, that delayed this process for SegWit's activation. So when you're using BIP9, you're supposed to signal for readiness. You're not voting to accept or reject a change. So once the soft fork is in the BIP9 process, once it's there, developers have assumed it's going to activate. They've done so much work already. They've re-engineered the entire code base, and it's ready to go. It just needs to be ready for industry to adopt the practice, right? Everyone's assumed it's going to happen. But miners interpreted this a little bit differently. They thought that this is going to be a vote for or against the protocol at this stage. This is their time to interact with the protocol. They're really supposed to vote before it ever gets to this point. The engineering effort is simply not worth it, and the developers should invest their time otherwise. The notion of having signals be this sort of free-to-do thing is kind of penny-wise because there should be a cost, but it's pound-foolish because it ends up making this big engineering delay for getting everything activated. And so how might we fix this? Well, we could use something from game theory called honest signaling. So in BIP9, it doesn't cost miner anything to signal yes or no, or even to change their vote, but we can impose a cost so that we know the signals are true. Now, if we don't do this, what do we get? We get this game of chickens. And so what happens is there's a face-off between have the developers gotten enough support from the miners to activate, are the miners signaling, so on and so forth. And these timeout, and this process actually makes for delay, because you kind of push for another round. So because the remaining amount of time is known, if you remember that state diagram, there's a case where we reject the change, and it doesn't ever end up activating. So behavior gets conditioned based on whether or not developers are panicked about this fork being adopted. And this creates a sense of urgency. Because as the timer runs short, there's urgency for those who want to modify it, who are making this trade-off on the change that they've pushed and that they really want to get, and another change a miner might request. So we can show this in kind of normal, Nash equilibrium game, that the thing that should happen if there's some benefit of a change to a developer and there's some cost of that change to the miner, and they have some requests that they could also additionally make, that nothing ends up happening. And because this is a unique solution, even if you play this in an iterated game, still nothing should happen. So no change actually ends up getting adopted, which is a kind of nice result. It's not a perfect result, but at least shows us that something is kind of wrong with this mechanism. That leaves us with a question, like SegWit did activate, so what happened? The answer is we really don't know. So it activated, but there were like 30 different things happening when it activated, all these different agreements, all these different things. So for whatever happened, we got it, but we don't actually, can't retroactively point and be like, this is exactly what happened. In fact, in the code base, what people end up doing is when a soft fork activates via BIP9, eventually they get rid of the BIP9 checking and they turn it into a BIP8 fork. They go, yeah, let's just activate it at this fork because it doesn't matter. It did activate. But I think that we'd like to fix this problem, and we'd like to have a method for activating a fork where we can point to more rigorously and say, here are the economic conditions that led to this thing activating. Here's how people had their right to express their vote. Here's what it cost them to vote. And today I'm going to propose to you Spork, which is sort of probably a fork. This is a mechanism for making these forks a little bit more incentive compatible when people do decide to activate. It's actually really easy to understand what happens. Every time we mine a block, the hash of the block, that's the main proof of work, we just add an additional proof of work, which is with the name of the upgrade that we're trying to do at that time. And so this is a probabilistic block filter. So 1 out of every some amount of blocks will activate based on this filter that I've written there. And that is not really gameable because the original proof of work is inside of that hash. So if you wanted to just grind on that using your existing hardware, the best you can do is normal Bitcoin mining anyways. So that's maybe a little bit abstract. Let's walk through a concrete example of what I'm proposing the flow of making a change would look like under this new rule. So I'm going to introduce this new operation that we want to get, which is check block hash verify. So we want this new operation, maybe because it's going to give us replay protection. It's going to allow us to invalidate transactions if there's a fork or if there's a long reorg. We can say, yeah, don't reuse that transaction if something weird happens on the network. But this requires some complicated changes, so it's going to take a little bit of engineering effort to go through. Someone will go ahead and draft a BIP which says, okay, here are the semantics. We're going to take this NOP8 and we're going to turn it into this operation, check block at height verify. And we're going to set the expected activation of the rule to be 6 months. And what that looks like in our probabilistic block filter is that the hash of the block and the string concatenated to it, check block at height verify over 2 to the 256 minus 1 should be less than 6 months of blocks. Now it goes into a feedback loop. So what we should do is we've defined what we want this change to be, but now we should collect feedback from the community. Hey, what do you actually think of this? And what should happen, hopefully, is they would catch that there's a bug. They would say, well, actually, when you introduce this new feature, you introduce an unintended side effect of being able to parse the block header inside of a transaction. So let's do some new mechanism that accomplishes the same goal, but without this downside. And so the solution in this case, it doesn't really matter for this talk, but you would do a non-SHA-256 hash, and that would address this issue. Once it's gone through this feedback loop where people have raised all their possible concerns, then we put it into a reference implementation. And we'll implement it and say, I think this version's passed, but version 0.18, and we'll do backports of this feature onto the last couple of versions. So if you're depending on specific behavior or APIs available in an older version, you don't lose that. You just enforce the new rule. Then here's what the rollout looks like. It starts at block 0, or with some offset, and we expect it to take 6 months to activate. After a few blocks, how much time do we expect it to be? Still 6 months. At a certain point, it actually does activate, and that's where I've drawn the dashed pink lines. Those are blocks that activate the new rule. But at any time before that, we still expected it to take 6 months for it to activate. So let's do some basic analysis on this, and we'll do a little bit more of a rigorous analysis later. By the time an upgrade is on Spork, so it's in the software, we've kind of reached this rough consensus. We have an idea of if there's support or if there's strong opposition for this thing. Every miner actually has the ability in this process to vote against the fork. And they can do this by refusing to build on blocks that activate the fork. and that should be like 1 out of every t based on 6 months. So 1 out of 6 months blocks will activate it. A miner can just say, I'm not going to mine on that, and that's their vote. However, this voting can be costly because it might require orphaning their own blocks. A miner's own blocks, 1 out of t of them, are going to activate the rule, and if they really don't want to activate it, they need to throw away their own block. This isn't a permanent problem. You might be thinking, but what about all these lost blocks? Isn't this bad for the network? Bitcoin has difficulty adjustment, so eventually, if we're abandon a fork for a very long time, it's just going to manifest as a change in difficulty. And I would guess with a parameter like 6 months, it's going to be well within the variance of hash rate anyways. Every miner has a large incentive to want to activate the fork. When they mine that block, if they don't want it, they're throwing away an entire block reward. They've spent a lot of money on the hardware, on the electricity, on the data center cooling costs, et cetera, to get that block, and they have to throw it away. So they really don't want to do it unless it actually means something. There's no influence for influence's sake. The probabilistic filter is an independent trial process, so it's time invariant. The expected activation is constant. So for all time, we expect it to be in 6 months. Now, we actually do get kind of a conditional information outside of this where if we expect it to be 6 months and it's taken like 100 years, we're probably pretty sure people are just politically opposed to it. But we let this emerge naturally. We don't force it to happen via a direct vote. And what this means is that making someone wait doesn't gain a miner any influence. So a miner doesn't say, I'm more influential, look at this block I threw out, because it doesn't give them the ability to vote for that in the future. So let's do a little bit more concrete numerical analysis of what exactly this means. So before and after the fork, we're going to say that a miner has some probability of mining a block. And what this recognizes is that a miner is probably opposed to a fork because it decreases their probability of mining a block. So at each step, a miner starts in the start node, and with some probability, they get 1 reward, and then they repeat the process. And we discount their next round with some discounting factor. Discounting has some support in the economic literature as like a reasonable model, especially exponential discounting like this. There are other models that you could plug in. Again, I'm not an economist, so I'm just using this as a model. If you want to model it using different things, be my guest. Under this, it's a simple geometric sum. So we see that after the fork, in the transient case, we are expected to be earning R times P active over 1 minus delta. And before the fork, we're going to earn R times P inactive over 1 minus delta. What is this discounting rate? Where does it come from? Well, maybe increased competition. We expect in the future there's going to be more miners trying to mine. We might think that our hardware might break. It might get too hot and burn out. Any secret advantage we have that's better than someone else might get well known across the market. Maybe we have a patented advantage, and now 15 years later, everybody has the same patented advantage. Or maybe we think that we have to convert into dollars, and we have some uncertainty of where the price might be in the future, and so we need to insulate against that, and so we discount our future profits compared to our current ones. A simple model to do this would be to look at the actual observed hash rate on the network and look at its growth over time. And if you do this, what you'll see is that it reasonably goes 2x every year. So it does grow currently exponentially. And based on that, we can compute what a per block discounting rate should be, which is this very big probability or discount. We don't discount that much for every step in our model. Within reasonable bounds, if we were to 4x per year, you can see what that value is below. Or if we were to only 1.5x per year, you can see the other value. If you have a decrease in hash rate, this model doesn't work as well, but I think it still does hold that you would expect more of your future profits if you think the hash rate is going down. What are P active and P inactive? Well, P inactive, so this is before the fork happens, should be less than half. If it's more than half, then it's not going to get the rough consensus when we're talking about it with the community, because most miners aren't going to want to get this. So we could estimate it by just saying as a straw poll in your Coinbase transaction, write a message if you're kind of okay with this fork, and leave it out if you're not. And we can take 1 minus the percentage of blocks that are signaling with yeah, we kind of like this thing, as our raw percentage that are opposed. P active should be less than, there's a typo there, but should be less than P inactive. We should be expected to lose something if we're actually opposed. If we were getting more, like that wouldn't necessarily make sense, but maybe there are circumstances where that could happen. And this represents the probability of mining, but it can also represent some other factors relating to just the core profitability. Now let's look at a miner who has basically a decrease in their probability of mining, what types of strategy they might have. We're going to discuss two strategies. One we're going to call the bad strategy, and one the good strategy. The bad strategy is one that's maybe socially undesirable, and the good strategy is one that I'm saying is socially desirable, but that may be, my own labels and not how the miners feel about it. The bad strategy, what I end up doing is I start at the start node, and with some probability, I mine a block. And if I mine a block and it doesn't activate the rule, I collect a block reward. If it does activate the rule, I throw away a block reward, so I actually lose one revenue. And then I start the process again. Now, there's also a chance, 1 minus P inactive, that the other miners mine a block. And so in that case, I don't get anything because someone else mined, but there's some probability, 1 over T, that they activate the fork. And then there's some probability, 1 minus 1 over T, that there is no fork, in which case I restart again from the beginning. But if it does activate, then we go into the world where the fork rule is applied, and now I get this transient state profit with P active. So one of the important assumptions here that I'm making in this model is that when it does activate, because we said P inactive is less than 0.5, you're not going to try and reorg that block. You don't have enough hash rate to do a sustained fight against it, so once it activates, it's going to activate. So we can analyze this state machine, and we can figure out what the expected value is from starting to traverse this graph. And it ends up being a little bit more complicated, but the same type of analysis as the earlier transient state. And we get some expression. It doesn't really matter exactly what it is, but it's an expression. We can do the same for the good strategy. And in the good strategy, what we do is when we get that block that activates, we're calling this good because we just go, okay, oh well, I had my run in the sun, and I'm going to activate this because everybody else kind of wants this. So here we go. And I agree to lose my higher P inactive rate. And we can analyze this all the same and get another expression. And so now we are able to ask kind of a core question, which is when is the expected value of the good strategy greater than or equal to the expected value of the bad strategy? And what this will tell us is that the miner starting this game, which again is an independent trial process, so it verifies for all time, that they would prefer to just activate the rule if it happens rather than to kind of go against the grain and orphan their own block, which might be a bad outcome for them. We wouldn't want to set things up so that the miner has to make that hard decision. We want to set it up so that the miner is okay with activating the rule even at a decreased hash rate. So we can graph this. We can actually graph this inequality by saying good minus bad and seeing what that is. And so you can see that you actually get some kind of interesting results. So what I'm showing you is I am showing you on the x-axis the P inactive, and on the y-axis the P active over x. So I'm just showing you kind of that expresses something that is a percentage of what the P inactive is. And what you see is that there's kind of a wall. These parameters, this is for a 1-year expected activation and a discounting rate of 40% per year. So what you say is in 1 year, my hash rate is only going to be worth 40% of what it is today. You can then derive a, per the, delta, you can derive the per block discount from that. And what this shows you is in these circumstances, something under 10% of the hash rate can be opposed to a fork. That doesn't sound too good, so let's look at a different parameter. What if discounting is 80%? So this means that we expect our hash rate to only decrease in value by 20% per year. This is kind of surprising. What you see here is this is all red. This means in this regime, everybody is willing to adopt the new rule right away as soon as it activates. Nobody's throwing away their old block. It's a little bit counterintuitive. I had to look at these charts multiple times to make sure I understood what was going on. What this is suggesting is that because of the decay, miners who have a lesser decline in their future profits are more willing to accept a change, even though it hurts them more in the future, right? They have this longer time period where their hash rate is active at a lower rate, but because they end up valuing the things as they do, and you can look at these equations and kind of convince yourself of how it works more concretely, it ends up working out. So let's look at a couple other examples, and then we'll talk about how you can apply this result. So if you put it at 6 months, and you say that they're discounting to 20% in a year, you get kind of an even picture. You get, under 20% of the miners should be opposed, and then you'll get everyone activating faithfully. If you change that discounting rate, so if you increase it from 0.2 to 0.4, then again you see kind of a similar result where now everyone's activating. And I had to pick these numbers because I wanted to show you the transition. The transitions happen at different discounting rates. So how can we use this practically? Well, recall we said that this is actually a measurable discounting rate that we can kind of assume as a variable, and we can look at what happens under this exact discounting rate. So here with 12 months and discounting equals 1/2 per year, we see that actually there's a pretty good regime of activating. If under 30% of miners are opposed, then they actually will be happy with just activating the rule and not choosing to orphan their own block. And there are a lot of other models which suggest that Bitcoin is kind of unstable if we have more than 30% of miners thinking about one thing anyway. So with labels, you can also see there's something interesting going on in the far left of this graph, which is that there's an indifference region. So that white region, that's where miners don't really care. They don't care for either the good or the bad strategy, and so I'd like to think in the goodness of their heart they'll do the good strategy, but maybe not. So let's say that we wanted to improve this, and we want to say, let's get it even better. Just increasing the time, that actually makes things worse. The way that miners discount things, if we increase the time, and you can think through, it took me like an hour to kind of get the intuition of this, but as you increase the time, miners' time preference changes, and then they'll become more opposed to the change. And so there's a lot of room to fail the fork because a lot of miners are going to be orphaning their own blocks, extending it, and we've decreased the overall fitness of this fork. On the other hand, if we decrease it from a year to 6 months, we've increased the space of where miners are happy, and now for all values, it's profitable for miners compared to the bad strategy to do the good strategy. So when do we use this? Have I proven that this is ready to go? I don't think so. I've given some concrete evidence which shows that this actually does let us think about the variables at stake for a miner and how we might model it and how we might change the activation timelines for a protocol change, how sometimes making the timelines longer messes with miners' discounting rates, and that we might counterintuitively not want to give miners sufficient time. We might want to put a little bit of time pressure, but allow them to organically vote on it indefinitely, because that makes it more compatible for them to activate it if they don't mind either way. There are also extensions that are worth exploring that make it maybe easier to apply in practice, and I've only modeled this theoretical version, but in practice you might want to have a couple of these things. I can just explain really quickly with the time remaining. So one thing you might want to do is you might want to say that the rollout of this thing can't happen before a certain height. In my model, it's completely independent. It just happens whenever the probabilistic filter is matched, but that's a little bit unreasonable because people do need some amount of time to activate. So you might say the probabilistic filter starts a month from now, and everyone upgrades and is ready and they have it, but you don't want it to necessarily start as soon as the binary is released. You might also want to put in an n-block phase delay, which might say, after this block activates the thing with the probabilistic filter, wait n blocks before the thing actually happens. This is for an exchange customer where the independent trial that activates it happens in the middle of the night in their time zone, and they've got to wake up all their engineers to go be ready to make sure the migration happens correctly. You don't really want that, so you might want to say, let's have it be 1 week so that there's a little bit of time for everyone to just be ready and flip any manual flags they have to flip. You might also want to do an n-block pass enable. So you might want to say, after n blocks pass the threshold, then enable the feature. This is a little bit like a firing squad arrangement where no individual block is really culpable for the activation of this. It's just a number of blocks that end up activating it. And so the first couple miners to participate in this don't necessarily have as large an incentive to orphan their own block. And this reduces variance and gives us more warning without having to encode any concrete timeline. You also might want to have an early adopter rule. This is a little bit interesting to model. If the activating block itself is not compatible with the new rule, invalidate the block reward of that block. And what this would do is this would incentivize everyone to have compatibility earlier, because you might end up mining an invalid block if you are generally planning to go ahead with it. So the soft fork rule could take place even before, take place and be enforced by most miners even before this fork is completely activated. Lastly, you could do an orphan-proof activation where just the existence of some block that activated this at some point would be sufficient for you to make your own block one of the ones that activates. So if someone did have enough hash power to temporarily turn on to reorg out that block that activated from someone else, you could then use this mechanism to just reference it, and I would leave discussion of that to our session chair, because he knows all about referencing ancestor blocks that get orphaned. Lastly, in a rich tradition of mentioning other events that are happening at events that are currently happening, this conference was announced at the last Scaling Bitcoin, and now I'm announcing the next Scaling Bitcoin, which will be in Tel Aviv, September 11th and 12th. So I hope you all can join us there. We're also going to be having Bitcoin Edge, which is going to be a fantastic event if you want to get more in the weeds on how to actually build and engineer in the space. Thank you very much.
Thanks a lot for a very interesting analysis. Unfortunately, we'll take questions offline.
Sure.
Due to we ran out of time. Thanks a lot for the speakers, and see you tomorrow morning.